So this webinar series is part of RMP's ongoing outreach program. RMP's core competencies and expertise reside in EPA risk management plans, CalR programs, OSHA PSM, SAMS program development. We also specialize in HAZOP and LOPA studies, as well as hazard identification techniques, and also a variety of other process safety and regulatory standards and regulations. We are here to assist any client who prefers to utilize a consultant with expertise and competencies in these areas. RMP's main objective is to share some of the insights acquired over the years so that each person viewing this webinar can manage their programs more effectively and administer evolving regulations into their programs. All right, moving on. Today we'll be covering the effects of control philosophies on operational safety. So typically, control philosophy is developed during the design phase of a project. So over time, though, original documentation tends to get lost, or what happens more often is that there are physical changes to a process that are simply not captured anywhere. I've been to a lot of facilities, and as I said, over time, you'll notice that the piping instrumentation diagrams have changed, that control elements have been removed from the field. And so the baseline assumption for this webinar is that even though at one time you had baseline philosophies, they've probably changed. So what I really want to look at here is giving instruction and feedback on how to develop these philosophies, not necessarily from scratch, but using the documentation, the information, and the resources you already have on hand. That being said, we're going to go ahead and start with a description and a definition of the philosophies. In this, we're going to look at the elements. We're going to look at some tips for developing these philosophies. And then at the end, I really want to go through the relationship of control philosophies with pre-existing PSM elements. So to start off with, the first thing we need to look at is your process control system. So this is part of the process that is maintained by all the automated systems, and it consists of things like your automated system responsible for monitoring and transmitting process variables. So this extends to your pressure, your temperature, your flows, anything you're using that is going to analyze process parameters, transmit them to a logic solver or some other method of controlling these parameters. As I said earlier, this goes to control devices. So this could be local devices. For instance, I have an image of a Fisher level troll. This can also include your mechanical pressure valves, or it can be remote logic solvers such as your PLC. Finally, your control system, the logic solver is going to determine what needs to be carried out in order to maintain the process parameters that you have input in the system. And this is going to be done via your final control elements. And so this is things like your automated control valves or any other element that brings your process back in line. So the control philosophy provides a description of how all these elements at your facility tie in together, and it does it all in one cohesive narrative. So jumping in, description and definition. So the control philosophy provides your operations, your engineering, and your instrumentation specialist with the details about what is occurring behind the scenes in a process. This right here kind of represents the overview of a control philosophy document. What you're going to do is you're going to have, obviously you're going to start with a table of contents, a list of revisions. I do want to bring up that list of revisions again because, as I said, the whole reason a lot of facilities are now carrying out redoing these philosophies is that the revisions kind of got lost in the shuffle over the last 10 or 15 years. So what we want to have in there besides revision sheet, the meat of these philosophies, is we want to put in specifications for the major pieces of equipment that are used in the process. Here I'm talking about your vessels, your tanks, pumps, compressors. What this usually is, it's a description of first what's coming into the flow, what separation is happening in the field or in the plant, where's it going, and then as we delve down, we get a little more specific. We put tableized reference material so we can look at what is the design temperature and pressure, what is the sizing of the vessels, what are their tag names. A lot of this information is actually all already available in the header of your piping and instrumentation diagrams. As we go on through the process, we'll start going down and we're looking at it by piece of equipment by piece of equipment. Here we're going to talk about the inlet into a particular vessel. the outlet from there, and all the control elements that are going to maintain the process. We'll look at process parameters and operating limits. We'll also develop the expected responses from these control elements that are used in the process. And you also want to capture the safety systems and associated set points, as well as the functionality if these set points are ever breached. So by way of example, I put together a very, very simple diagram. This is a free water knockout drum that I'm naming V-101. You can see here I've got my inlet flow coming in. I have my outlet flow from the weir. I purposely did not include the vapor flow out of the top or the water flow out of the bottom. Like I said, this is simply for an illustration as I kind of give an overview of how I generally will develop the wording and the description in my control philosophies. Here I am unfortunately going to read directly from this slide. So I start with an overview of this vessel. The free water knockout vessel, V-101, receives produced fluid from the upstream production header via inlet valve at the north end of the vessel. Separation into free water and emulsion layers occurs as the produced fluid moves through the vessel. The oil is decanted by weir at the south end of the vessel. Gas is stripped from the top of the vessel, and water is moved from the bottom of the vessel. For the sake of this presentation, I also noted that they're not pictured here. Obviously, if you're developing a full control philosophy, those items would be shown on the schematic. So now we delve a little bit deeper. Now we really want to look at the control. What is occurring here? So once again, just looking at the inlet flow. The inlet flow is controlled by a fail-open inlet flow control valve called FCV101-1. Flow rate is set manually by operator via the HMI. In the event of a power failure, the flow of instrument air to FCV101-1 would be shut off by the associated solenoid valve, SB101-1, so that FCV101-1 would fail open. It's kind of wordy, but if you look at it, in this you can see I've pointed out the basic functionality of the device. I've talked about the interaction with utilities, and I've noted the fail state. So moving on to some of the more instruments that we'll see in this particular unit. Now we want to talk about the level. Once again, I'm not going into the interface level here. I'm really looking at what's going on in the weir. This is a statement that I would put into the philosophy. The level in the weir is monitored by level indicating transmitter LIT101-2. The level is maintained via PID loop configured to open level control valve LCV101-3 in order to maintain the level at normal operating levels as set by the operator. LIT101-2 has an associated high and low level alarm. These are set at 3 feet 6 inches and 6 inches respectively. These will both activate an alarm at the HMI to alert operations to level deviations in the vessel. Once again, there are safety features associated with this particular control device. I have stated that in the wording and in the text of the control philosophy. So that is wordy. It's a complete description. It's a narrative, once again, focused on these two particular inlet and outlet flows. But of course, we also provide reference tables that are going to let someone be able to quickly access this information. So once again, here's a quick look at an instrumentation table. We want to note that a description of it. So we're basically saying here we have our control for LCV101-3 and our control for FCV101-1. We note that the instrument that is providing this control is the level indicating transmitter LIT101-2, and we note the set point. We also note for the other instrument, this is actually set at the HMI, and it will vary based on what operations have to set that period. Next, we look a little more at our safety systems. This is a little more extensive table, but it still captures the same basic information. We want to look at our device, our transmitter. This is what's going to send the signal. We want to give our alarm tag numbers. We have our level alarm high, which is designated as an LAHH, a level alarm low, designated as an LALL. We include our set points so someone can easily reference, hey, this is where the alarm is going to function at. We put the action, for here is simply an alarm. Then we give a description of what happens when that alarm triggers. V-101 emulsion level alarm high alerts at the HMI when the level exceeds the set point. It's simple, but someone can reference it quickly. As I said earlier, I didn't include the other outlets from the vessel, but I did want to include, for instance, if you did have the gas outlet, you'd most likely have a pressure indicating transmitter with associated pressure alarms. So I included these. Also mainly because I didn't want all my actions just to be alarms, so I threw in an alarm and valve closure. And those actions can vary from saying things like alarm slash valve closure to alarm and trip. And once again, you'll use your description, as I did here, B-101, high pressure alarm, alarms at the HMI when level exceeds a set point, and shuts off supply to the vessel by closing the upstream header control valve. Like I said, if it had been a trip, you want to state everything that is going to happen when this particular safety element activates. What compressor it trips, what valves are shut down. This is kind of a one quick look to figure out exactly how your safety systems are operating in the field. So, by way of reiteration, the elements of a control philosophy. First off, you have your table of contents and revision sheet. You're also going to have your description of the overall process. This is a very important key component. You want somebody able to read this, similar to looking at a process flow diagram, but in words, and understand exactly what's going on in your process. You also want information on the major pieces of equipment used in the process, and this is generally tabled. A little bit easier to read, a little bit easier to take the information required. And then you want to delve a little bit deeper into the details. You want equipment-specific process overview, and this is going to include the details of the process, your inputs and outputs, your set points. You're going to keep reference tables for process control and alarms. And you also want your design basis in there. So that was, like I said, a very quick overview of what is contained in a control philosophy. What I want to do now is just give some tips for development, some of the things that I need to do when I go out in the field, and I try to develop these for a facility. I was actually at a PHA a couple weeks ago, and I was talking to their control specialist about control philosophies and what he does to develop them. And he pretty much said he tries not to. He said that usually if you want to develop a good control philosophy, you pretty much need to live in the field for about 6 months to a year. Through my experience, he is close to right. I do spend quite a bit of time in the field, but these are also some of the documents and the information gathering tools that will help to reduce some of the time spent putting together all the information you need. So starting off with piping and instrumentation diagrams. I already mentioned this. That information almost directly correlates to your process overview table. It's where you're going to get most of your information from. Generally, that information is not changed too often over the life of the facility. And there's usually documentation you can follow along to figure out where these changes have occurred. Process flow diagrams, as I mentioned earlier, for the process overview, it is almost simply a wording of what you see in a process flow diagram, a little bit easier for operators or anyone out in the field to read and understand what's going on. UNA forms for pressure vessels, obviously that's going to provide information on your vessels out in the field. It's going to be included in your process overview. Any original design documentation. And obviously, as I said earlier, this has changed or may have changed extensively over 10, 15 years, 20 years of operation. However, I love looking at the old design documentation. It really gives you a feel for why the instrumentation was originally added, what original set points were included, and then you can kind of get a feel for why it may have changed over the years. Vendor O&M manuals, obviously you're dealing with a pump or a compressor. This is going to give you the most information on what is going on with that particular piece of equipment. Site walkdowns. As I mentioned earlier, living in the field, and I can't stress how helpful the site walkdowns are to really get a feel for what's happening with units. We spend a lot of time looking at piping instrumentation diagrams, and sometimes you don't quite get the scale, you don't quite get the interaction of units together out in the process. So I usually like to take my PNIDs, walk through the field, check all my lines, check all the instruments on there, look for any deviations, any differences, and really get a feel for the scope of the process. So once again, I do spend an extended amount of time in the field just looking at the units and verifying that the paperwork I do have is accurate and up to date. Finally, personnel interviews. I have a saying, engineers know how the process is supposed to work, operators know how the process really works, and of course you have your instrument control specialist, and these are the guys who can look right into the programming and tell you, no, here's what the set point is. So maybe it changed on the PNID, maybe an operator tells you, oh, well, I think it's around 3 feet. This is the person who's going to look right into the program and go, no, it is 3 feet, 2 inches. That is where your alarm triggers. So having discussed the basics of the control philosophy, also some tips for development, what I really want to cross over now is kind of the thrust of this webinar was the effects of these control philosophies on general process safety. And to do that, I wanted to show the correlation and the overlap between control philosophies and with PSM elements you might already have at your facility or might be actively developing. From a safety perspective, there's so many points that intersect. I have a graphic here. So you have a control philosophy. You can obviously see it touches your PSI, your process hazards analysis, your management of change program, standard operating procedures, mechanical integrity, and your training program. Moving into these elements, I want to start off with operating procedures. And the reason I want to start off here is, in my mind, the control philosophies exist side by side with the operating procedures. And this comes from experience of reading a lot of different philosophies from a lot of facilities that have evolved over the years. And it used to be that you would have one single document that would say, well, here's the automation going in the process, here's what the operator does. And it did provide a good scope of information, but over time we've realized that operating procedures work a little bit better in a step-by-step manner. So that someone can take it out in the field and go, hey, I turn this valve, I press this button, this is how I get the process working. I don't necessarily need the details, the automation going on in the background. However, I've never heard anyone say that too much knowledge is going to be a detriment. So, as I said earlier, we try to have them be side by side. Put them together, you should be able to get one very good scope, one good idea of how the entire field is working. Operating procedures are good for in the field, walking around. Control philosophies are a little bit better for just reading and understanding the process. Based on that, we should go and look at training. As I said earlier, control philosophies are an item that should be looked at and kind of absorbed prior to even going out in the field. Control philosophy is to provide the personnel with working knowledge of how the automation controls the process, maintains the process operating within its design intent. It actually makes a very good addition to your training toolbox. You can, let's say, give them operating procedures, and even though they might not need to make direct contact with the automation, they most definitely should know what is going on with it, especially in the case of alarms. During PHAs, we bring this up a lot. If an operator hears an alarm, do they know what the alarm is? Do they know how to respond? If they don't know what the alarm is, the time taken to discover what that alarm means might actually make a difference between a very large disaster and something that's easily mitigated and solved before it goes to fruition. Process safety information, I think it's kind of intuitive that there's going to be a lot of overlap between a control philosophy and your process safety information. I've already mentioned we're going to have our equipment specifications. We're going to have listings of our safety systems, which these are both requirements of a PSI program. You're going to have information pertaining to the technology of the process. What's good about these is they kind of bounce back and forth, and you can feed off each other. If you've already got a control philosophy developed, there's your documentation. That's what you're putting in your PSI. If you already have a well-developed PSI, you get to steal from there and put it in your control philosophy. Process hazard analysis. This is where I really first started coming in contact with control philosophies. And over time, I've managed to build quite an extensive library that I kind of look through. I look for elements I like, things that make sense, ways to develop these that provide the most effective tool for a facility. So some facilities I go to, they swear by them. They say, if it's in this philosophy, it is in the field. It is the Bible. I've actually heard that quoted in certain studies. Unfortunately, other facilities I go to will say, well, it's in the philosophy, but we really need to send someone out there in the field to make sure this is true. I actually think having no documentation is slightly better than having incorrect documentation. Because once again, if you have no documentation, someone's going to go verify it. However, if you have incorrect documentation, you're going to make decisions based on that incorrect documentation. Some other helpful items that the control philosophy helps with during the PHA is you get details in your control loops. You get to look at your safety systems. You get a good overview of your basic process control system. I brought up earlier the wording, and I showed you in that example. If you look at that wording, it's actually very similar to the way I would word a safeguard in a PHA. I look at the device. What does it do? What's its tag number? Where is it located? What's its response? What are its set points? All those are elements that you'll also see in a control philosophy, so you can definitely see the overlap between a PHA and these philosophies. Management and change. Management and change, some facilities are great with it, some are not. Usually you have a checklist, and it says things like you need to update the P&IDs, you need to update the operating procedures. But what the control philosophy does, it lets you know that what change you do, how it affects other units in the field. So you can sometimes be focused on your piece of equipment. Hey, I want to remove this pressure control valve from this tank. But what you don't know is, well, removing that pressure control valve, what's that going to do to the downstream compressor? What's that going to do to upstream equipment? This gives you a very good overview so you can sit there in this pre-design phase and help to make your decisions in ways that will make your process run the most effectively and the most safely. Basically, the control philosophy is kind of a one-stop shop for all your process information. The mechanical integrity program, once again, I think this is intuitive. You know, mechanical integrity deals a bit more with frequencies of maintenance and looking at your equipment, but you really want to look at how each of your pieces of equipment responds in the entire process. Looking at a single compressor sitting in the field, you can think about the maintenance on that, but you really want to know, what does this compressor have to do with my upstream equipment and downstream equipment? What pieces of control elements are controlling the flows into here? And this can actually color your maintenance activities and give you an idea of how important one piece of particular equipment is in your process. So in conclusion, you know, we've looked at a basic definition of process control system and how you would develop a control philosophy to describe this system. Obviously, control philosophies are much more developed, much larger documents. I had given you a single vessel, and I had only given you one inflow and one outflow. This vessel alone has two more flows, different phases, different control elements, temperature alarms, pressure alarms. So as you can see, these control philosophies can be very developed, very convoluted. I guess convoluted is a bad word, but very detailed. And you want that to be. You want to be able to read this, and you want to say, look, I can read this almost like a book and tell you what's going on in my process out in the facility, out in the field, or wherever it might be. So control philosophy provides a description for all the automation elements responsible for maintaining operation of the process, and it's done in one cohesive narrative. The control philosophies intersect with multiple PSM elements. The majority of the information is already available at the facility. Once again, you can pull from your previous documentation and probably get a lot of the information you need. What you can't, that is where the field walkdowns and the personal interviews are going to come in, and especially building that relationship with your instrument control specialist, getting into the programming, and really look at what is happening with each control element. The control philosophy is a living document. Like a lot of the PSM elements, it needs to change as the process changes. I stated this at the very beginning. You probably have original control philosophies, but somewhere it fell by the wayside, and so now they don't really mirror what's going on in your field. Keep updating it, and you'll have a very strong document, and then over time, in the future, this is going to alleviate a lot of the other documentation you need to prepare. You'll be able to access this information easily. Control philosophy is also useful for determining the necessity and the consequences of changes to a process. I brought that up when we talked about PHAs, MOCs. Once again, one-stop shop for all your information of what is going on in your facility. From here, we're going to go ahead and end the webinar, and I am going to wait and look for any questions you guys might have.
The first question is, we are in the middle of developing new PSI procedures. I'm having a control narrative as part of the safety systems documentation. It seems these used to be called the EPCS narratives. Is the control philosophy a new name for the control narrative?
Yes, in fact, I meant to say that at the very beginning. I use control narrative and control philosophy interchangeably. In fact, I actually like saying narrative a little bit better, but they are the exact same thing. The difference is if you look up the control plans, which were kind of tabled versions, which were developed about 10 or so years ago, those are useful, but they do not provide the information of a control philosophy or a control narrative.
Next question. Is there a specific regulatory requirement for a control philosophy? And would a cause and effect diagram satisfy the need for a control philosophy package?
So there's not a regulatory reference. I have looked, and everyone develops them based on their needs, but there is not a particular regulatory reference or a standard that I can cite that drives these documents. in regards to the C&E contains the essential information that you'll see in the control narrative. Once again, I like the narrative a little bit better because the narrative is a way to not just get that information, not just get the tables, but to actually read and get an idea what's going in the process. So C&E is useful. Once again, there's not a regulator who's going to come to your facility and say, well, you also need the narrative. But in my opinion, I would also say develop a good control narrative alongside that C&E, and you have a good feel for what's going on in your process.
Do you think that the control philosophy should include non-automated control elements like manual operator functions?
No, as a general rule, I don't include those, and some facilities actually request them. They want to know what the operator is going to do as well. But generally, I keep that in the operating procedures, and that's why I said earlier they go side by side. Operating procedure should include all the operator touches. The control narrative should include what the automation is doing. They should be read together, but I think if you put them in, the document itself becomes so convoluted, it doesn't become useful for either party. An operator is not going to take a 300-page document in the field to learn how to turn on a pump. Someone reading the philosophy is trying to get a feel for the process flow. It's useful information to know what the operator is doing, but it's generally not essential unless it interacts some way with the automation that could result in a hazard or a process upset.
So in reference to your example, are you using a high-pressure trip to protect against a liquid overfill? Do you expect that the high-pressure trip will have enough time to react?
Typically, high-pressure trips, I do expect to have enough time to react. I purposely left out a lot of the other pressure controls in that I had the pressure transmitter, and this example I made is somewhat of an amalgam of many different vessels I've seen, because obviously we have trade secrets issues, and so I did not want to grab a specific vessel or a control philosophy from any of our clients. So this is somewhat of an amalgam, and so that's why I really stuck to somewhat generic responses. So I did the level increasing high, and so I just had the downstream valve shut down. I made this assumption that there are other outlets, so I was not hurting upstream pumps. But yes, definitely for the pressure trip, you would see a shutdown. In my mind, you need those trips to act fast enough for pressure. You can usually do an operator response to level, but with pressures, I don't trust anything besides trips.
So this is in response to your previous answer concerning the regulatory requirements associated with the control philosophy. I think the OSHA asks you to maintain updated safety system documentation as part of the PSI documentation for a PSM process. So in that way, there is a regulatory requirement. Any thoughts?
Well, yes, actually that's perfectly correct. However, usually the safety information in the PSI is a document in and of itself. So to my mind, that actually contains all the regulatory required information. The control philosophy, to me, is slightly above and beyond that. However, you can do references back and forth. If you have your PSI section say that EPA or OSHA, the CalARP inspector is going to look at, you can reference the control philosophy as long as it has all the required information. But generally, if you don't have a control philosophy, obviously we do compliance audits, and so we ensure you have a well-developed PSI section that's going to answer regulatory framework.
That's about it for questions.
Okay, thank you very much for watching, and hope to see you again.